So this one's pretty straightforward. They just give us this diagram. The find, though, is important because, again, that influences what are we taking as our object of interest, what are we isolating from its environment. So in this case, we want to know the horizontal and vertical components of reaction at the supports. So in this case, there's a support at A, a pin, and a support at B, which is a roller or a ball. It'll act the same way. So we want the reactions at A and B. So for our free body diagram, the first thing we need to do is determine what is the object of interest. What are we isolating from the rest of its connections and representing what forces act on it, what moments and couples act on it. So in this problem, again, it's not as obvious always as it was for particles. What's the object we want to isolate for this problem? Yeah.
The beam.
Right, so the beam specifically, so just like the brown part, the wooden beam. And we want to pay attention to what are we keeping in our system and what are we excluding in our system. So I'm modeling the beam. The thickness of it for this problem is not going to matter, so just a simple line here. So notice, what am I not including? I'm not including the pin. I'm not including the roller. I'll have to model that of what they do to the beam, but only the wooden part of the beam is included in my picture. So I want to dimension it out. So I have this point B. I'll call this point C for convenience, and point A over here. So I have the beam, and I have the length of all of its components. It's just, it's only a horizontal structure, so 5 feet from A to C, C to B, and then B to, I guess I'll call it D just so it has a name. So I have my object. So to isolate it, I have to, because I didn't include the pin, I didn't include the roller, those effects will have to be modeled on my structure, but I'll wait for to put that in for a second. So the next thing I want to do is I want to look back at my original, in this case the diagram. I want to just copy exactly the applied forces, because those will come with it. So any applied force that's on the object that I chose comes along for the ride. So I have this 500-pound force acting on my beam at a 3-4-5 ratio triangle. And I have this applied couple acting at what I call D, 600 pound-feet. So now kind of the new part of what we have to look at, I didn't include the pin or the roller, so I have to see what do those supports do to my beam. So one support at a time, I want to consider what motion did that support prevent from happening for our object of interest. So let's look at B first. It's that roller or that ball. So if you imagine the ball on the ground, if we took our beam and we wanted to move it left or right, would it be freely able to do that because the ball is there?
Yes.
Right, so the ball allows it, so there's no force left or right. Now if we think, because the ball is there, can we move our beam up and down? Right, we can move it up because the roller is going to be, or that ball, really is just going to be a normal force. It prevents us from pushing it down, which means that the ball exerts a force up on our object. So we know the direction of this has to be up because it's basically a normal force. So we know it has to be up, but for sure it's along this axis, this vertical axis. So I know its direction, but I don't know its value. I'm going to call this By. And then if we think about rotation, so about point B, can the beam rotate about the z-axis at point B? Right, so the ball does allow that, even if it's just a little bit, it does allow it to rotate if it wanted to. So we don't put a couple at B. So the only reaction we have is By because it can't move down into the ground. While I'm at it, I will have a coordinate system. So B is done. Now we ignore B and we look just at A. So A, we have that pin connection. Again, we're going to encounter this a lot, so it is pretty standard, but just to go through the details of it. So because it's pinned at A, can we move it left or right? Right, so it prevents that. So I'm going to call that AX. And can we move it up, down? Right, it can't move up and down, so we have an AY. In reality, it can't move along any axis. But yeah, if we look at how we model a pin, in reality what it's doing, we could do this at the end. In reality, it's going to be exerting some force at some direction. But again, I'm going to break it already into components. If I wanted to at the end, I can go back and put it into polar form. But starting here is going to make it tougher. So a pin we're going to model as a horizontal and a vertical force. And then again, because this pin is here, can the beam rotate about the z-axis at point A? Right, that's kind of the design of the pin. It can freely rotate. So if we look at our free body diagram, we don't know AY, AX, BY. We have those applied forces. Everything's labeled, and we have a coordinate system here. Any questions about the free body diagram?
We show a couple on the diagram or not?
Yeah, so here's the couple, 600 pound-feet. So couples or applied moments have to be included on your free body diagram.
If BY and AY and AX are all the forces, why is BY going towards B, but then AY and AX going away from it?
Oh, that's just how I drew it. As long as it's, all that really matters is the line of action. So if I drew it down here or if I drew it like that, it means the same thing. So I tend to just draw it for normal forces below the beam, and for a pin, I draw it coming out from A. But the way you draw it, as long as the line of action is correct, is what's going to matter. Other questions on the free body diagram? So again, I'm going to be stressing free body diagrams because your free body diagram is going to dictate what we write for our equilibrium equations in the next step. So we're in 2 dimensions. It's a rigid body. So remember, we get 3 equilibrium equations out of it, not just 2 that we saw for particle equilibrium. So the first steps are going to be the same that we saw for particles. Sum of forces x is 0 because it's an equilibrium. So what's my right-hand side going to be for this based on our free body diagram? Right, 3/5, 500, which is also to the right. These are both positive. They're both to the right. The couple does not appear in force equations. By is only in the y. Ay is only in the y. So this is my complete right-hand side. And if I look at it, I could save this or do it right now. For my one equation, I have one unknown. So right away, I can solve for ax if I want to. So in this case, negative 300. And if we look at our find, that's one of the things we're asked to find, the reactions at A and at B. At A will have 2 components, and at B will have 1 component. Right, so I happen to have one equation, one unknown, so I solved it right away. Now I can sum forces that act in the y direction. So what's my right-hand side in this case? Right. So in equation 2, I have 2 unknowns. I've already used my equation 1. I can't get a number here yet, so I'm going to save it for right now, and I'll come back to it later. Because remember, I have 2 equations. I have a total of 3 unknowns. But yeah, it's a rigid body. We get a 3rd equilibrium equation out of this. So now we can choose the sum of moments around any one point we want. So I'll indicate that in a second here. This is where, again, it doesn't matter which point we pick. As far as having linearly independent equations, it matters which point we pick so that the work for ourselves is the least. So if we come back to our free body diagram, I've labeled here A, C, B, and D, but I could choose any other point. But of these 4 points, if I look at point A, the reason pins are good to take the moment about is because if we look at AX and AY, both of their lines of action pass through A, meaning that neither of which appear in the moment calculation. So these are two things I didn't know, but now in my equation 3, by picking A, neither of those unknowns are going to appear in the equation, meaning there'll be only one unknown to solve for. If I chose point C, it's still going to be right, but at point C, by will be in the equation and ay will be in the equation. So just by hand, it makes it a little bit tougher to solve that way. So I would suggest choosing point A to take the moment about, counterclockwise being positive. So if I decide to choose point A, what is the right-hand side of my equation 3 going to be? All right, let's say one component at a time. So I heard the 4/5 part. So the vertical component of that applied load of 500 is the force. So right, times 5 is its moment arm or its perpendicular distance to A. Is that positive or negative around A? So again, if we envision this pointing down here, so holding at point A, if we push down here, the whole object would want to spin clockwise around A, making this a negative moment around point A. And the horizontal component of the 500 has its line of action pass through A, so it will not appear in this equation since its moment arm would be 0. So I just won't write it. All right, what else needs to be on my right-hand side? Right, so a force of By, a moment arm or a perpendicular distance of 10, and this causes a counterclockwise moment around A, so it's positive. So right, 10 By, right, minus 600. So again, don't be careful with the couples. By was a force, this 500 pounds was a force. The 600 is already a couple. So again, I want to reiterate, we don't multiply this by a distance. Whether it was acting at D, or C, or A, or anywhere else, it would be the same negative 600 in this equation. So even if it was at A, just because a force that acts at A is not in the equation, a couple that would act at A would be. So it's already a couple, it's already in pound-feet. This is in pound-feet. This will be in feet. We're going to get an answer here in pounds. So the 600 is already a couple. It doesn't get multiplied by a distance there. So just that 600. Questions on equation number 3. So that's everything that causes a moment around A. Again, it's in equilibrium, so this is equal, we know, equal to 0. So by the nature of choosing point A, I've eliminated my two of my unknowns, so I can solve this now directly for By. So By, I get 260 pounds. I can put that then into my equation 2 and get my last unknown. The Ay is 140 pounds.